In this video, let's talk about how we can use integrals to help us find the area, volume, arc length, and surface area. And these right here, you definitely have to know them for your Calculus 2 class. Let's talk about the area first. Let's say we have y is equal to f of x, and I want to find the area under the curve from A to B like so. So it's this region that we are talking about. First, we are going to start with a rectangle, like so. And it doesn't matter if you have a left endpoint or right endpoint, because this rectangle is supposed to be really, really thin. Now, let's talk about how we label this rectangle. The base right here is just a small change in the x, so we'll label that as dx. And the height is from here all the way up vertically, so that's the y. And if you want to find the area of this rectangle, it's just simply y times dx. So let's put that down. And this right here is just a small change in the area, so we can say that it's dA. Now, if you want to get the area of the whole thing, we just have to add up all of this kind of area, and we do it by the super version of addition, and that is the integration. So integrate, integrate. So from here, we get our area, and that's just the integral. And notice we have y, which is not allowed in the x world, but it's okay, because y is f of x. So let's just replace that right here. And then dx is just dx, and we are in the x world, so keep in mind x going from A to B, so I'll just put this down right here. So that's the formula for the area of that region. Now, suppose we have x is equal to a function of y, so the curve might look like this. It's no longer a function in the usual sense because it does not pass the vertical line test. But suppose we have this curve. I want to find the area from here to here, C to D. So it's just like a horizontal region. And you will do this kind of things quite a lot back in, like once you are in Cal 3, not back in Cal 3, but once you are in Cal 3. So how do we do it? Well, we can just turn the rectangle sideways, right? So let's go ahead and do that as well. So I will put this right here. We'll have a sideways rectangle. This time, that is the small change in the y, so that's dy. From here to here, it's the horizontal distance, so that will be x. And then we want to find the area of this red rectangle. Again, it will just be x times dy, and that is just dA. And you want to find out the whole thing, then just go ahead and add them up by using integration. And then we will just get the area equals the integral. X is not allowed in the y world, but it's okay. X is just the same as g of y. And make sure you pay attention to the c to d in terms of the y values. So c to d, and we are done with this. Next, let's talk about volume. In particular, we're focusing on the disk method. And if you have a lot of disk, then they just look like a cylinder. If you have one of them, this is still a cylinder. So let's talk about the volume of a disk, which is really just a volume of a cylinder. And you need the area of a circle, so that's pi r squared. And usually when you are talking about the volume of a cylinder, you talk about the height. You will have to multiply by the height. But here, because the height is so small, let's call this thickness, multiplied by thickness. All right, so here's the situation. Let's say we are going to take this region and rotate about the x-axis so we can generate this solid. How do we find the volume of this? Well, we are going to start with a rectangle just like what we did earlier. And then just like what we did earlier, this right here is dx, and this right here is y. Now, if we take this rectangle and rotate about the x-axis, that's how we are going to get a disk right here. And then let's pretty much put down the same label because this height right here becomes the radius of this disk. And then the base right here becomes the thickness of this disk, which is dx, just like that. Then we can just use this formula to find the volume of this red disk, which we have pi r squared, so we have pi y squared, and we multiply the thickness, which is dx. And this is just a small change in the volume, so what should we label this? dV, yes. So we can just put down dV is just that. And now once we have this, yes, just go ahead and add up all these kind of disks, and I will just integrate, right? Integrate both sides. So we get the volume is just the integral, pi is just the pi, y, it's not allowed in the x world, but it's okay because y is just f of x. So we can say f of x, and then let's square that, and then we are in the x world, and x goes from A to B. And that's the volume formula for that situation. Now, let's take a look. If we have x as a function of y, and then this time we are going to rotate it about the y-axis, so it's like a horizontal case, then we end up with this kind of solid. What do we do? Same thing. Yes, we are going to start with a horizontal cut for the rectangle. This much right now is going to be the dy, and the horizontal distance against the x. Rotate this horizontally. This time we will have a disk that looks like this. And as you can see, from here to here, which is the horizontal distance earlier, that's still x, and that is the radius of this disk. And then the thickness is the dy. So for this volume right here, we can write that down as pi x squared times dy. And once again, this is just a small change in the volume. So dV equals this, and then just integrate both sides, and we get the volume equals the integral pi x is the same as g of y, so let's replace that, and the square, and then dy, and y in our situation goes from c to d, and this right here will do it. Next, let's talk about arc length. In another word, we're just trying to find out how long this piece of the curve is. But of course, this curve we cannot just measure with a ruler, so what do we do? Well, let's use calculus. And for calculus, let's do it with tangent lines. Let's start with a point somewhere here, and I'm actually just going to draw a little tangent segment, but if I draw it too small, we cannot see it. So I'm going to draw it somewhat like this, so we can take notes with this, yeah? Well, you can see that if I really make this small, then this length and the length of the arc will be very close, yeah? So we're going to use this to approximate that. And then if we make it really, really small and then add up all the such lengths right here, then we'll be done. And that's the idea of integration. When you are trying to do something that you don't know, break it down into small pieces. Once you narrow it down, it will look like just a straight line. And then you tackle that. And then you add up all the results and you get the final result. But how can we find this length though? How do we label that? This time it's slanted. Well, don't worry. Because if you have a tangent segment, if you go horizontally, this right here is the small change in the x. So we can label that as dx. And then if you go from here to here, that's a small change in the y. So we can label that as dy. Now, this right here is a small change in the arc length. I'm going to write that as dl. Notice, some books might write it as d little s, but later on, when we do the surface area, we also use s. So let me just use dl right here. Once you get to chemistry, then you use d little s. Alright, now we have this, which is actually a right triangle. Right? Horizontal, vertical, right triangle. So what can we do? Pythagorean theorem. Okay, cool. So we must have dl squared equals this square plus that square. Very nice. Now, to isolate the DL, I can just square root both sides and take the positive version of it. So we get dl equals square root of dx squared plus dy squared. Good. And again, this right here is just a small piece of the arc. I want to find out everything, right? From here to here. So we'll have to add them up. And we do the super version, which is the integral. But now, here's the issue. Which world are we in? Are we in the x world or the y world? I don't know, right? Because we have the dx squared right here and then the dy squared right here instead of the square root. So what do? We do algebra. Check this out. Check this out. In fact, we have two possibilities. So, first way, we can look at this and then let's factor out the dx squared. So on the left hand side, we'll just have L. That will be equal to the integral, and then we look at the square root. I'm going to factor out dx squared. So this term will just be 1. And then for this term, because we took out the dx squared, so we will have to divide this term by dx squared. So we add dy squared from here originally, and then we divide that by dx squared, like so. Have a look. Here we have a square root of a product this times that. And of course, we can just take the square root of this, which is just dx by itself, and then we can put the dx at the end of the integral. So we will see that L is just equal to the integral. Let's have the square root. It's just 1 plus, and then we have, this and that both have the square. So I'm just going to put it down as dy dx. And then we square that. And remember, we have the dx right here, and let's put that on the outside here. So in this case, we are in the x world. So we are going to pay attention to the starting and the end in terms of the x values. So let's say they are going from A to B. This is it. But under what situation do we do this though? Well, here, as we can see, we have dy dx. This is the situation when we have y as a function of x. Right? And then you can just go ahead and do the derivative and then set it up. Now, what if we have x as a function of y? Well, in that case, I'm going to factor out the dy squared, and then the algebra is pretty much the same thing. So we have L equals the integral, and then we have the square root. I'm going to factor out the dy squared. And then here though, we will have dx squared divided by dy squared. Plus, this right here will be just a 1. Now, again, same thing, multiplication, so we can take the square root of this, and it will just be dy, and we put that at the end. So L equals integral, we have the square root, and let's put down the 1 first, so it matches with that form. And then again, same thing, we put a square on the outside here, and then we have dx dy. And this means you just take the derivative by looking at the x equation, yeah? And then we are in the y world. And make sure that you pay attention to C to D in terms of the y value. And there you have it. This is the R-length formula for that situation. Pay close attention to this because we need to use dl is equal to this, and then again, this portion here is the dl, right? This portion here is the dl. When we are given y is equal to f of x. Likewise, this is the dl. When we are given x is equal to g of y, because when we talk about the surface area, hey, this will come back again. Let's take a look. Lastly, let's talk about the surface area. Let's say we have this arc, and then we are going to rotate it about the x-axis, and we generate this kind of solid. This time though, we want the surface area that goes around this solid. What we'll do first is, we are not actually going to draw like a horizontal or like a rectangles because we have an arc. So we will draw the small tangent segment like what we did earlier. So I will do something like this, and we label that as DL. And then let me just translate that to here. And then again, we also do the rotation. So we will get something like this. This time though, notice because this is slanted, so this is no longer a cylinder or disc. So what is this though? Well, I will tell you. It's going to look like a piece. Alright, I will tell you. This right here looks like a part of a cone, right? Because if you look at a cone like this, and then if you just look at a portion of it, yeah, it looks like a portion of a cone. You just cut the bottom off. Now, here's a question for you guys. I want the surface area. So I'm going to go around here, or you can imagine if I make a cut right here and then open it. If I make a cut right here, right? If I make a cut right here and open it, what kind of shape are we going to get? Ready? First, imagine if we have a cone, which is what I have right here. Yeah? And I'm going to open it. Then we get a sector or like size of pizza. It kills my cutting skills of the paper. But this is just a part of it, right? This is just a part of the cone that I showed you earlier. So what I'm going to do is, I'm going to cut it off for you guys right here, right in front of you too. So check this out. This is this shape, yeah? Yeah? Yeah, yeah. Okay, and then I'm going to open it. So I get this kind of rainbow shape like this strip. So this is crucial because I have to find the surface area, which is the area of this thing. I'm going to draw that right here for you guys. And as we all know, this right here is not rectangle, but in fact, the area of this behaves like a rectangle. You just need to tell me two measurements. Tell me how long this is, the middle portion, all right, this right here, and also tell me the width right here as well. I'm going to call this W, I'm going to call this L. So the area right here is just equal to L times W. Now, let's get back to this case right here. What is our little l right here though? The little l is this portion here, but I will have to put this back for you guys, like this. Haha, we have a circle, don't we? The L is what? The L will be the circumference of this circle, if you look at it from this point of view, right? Yes. I know. I will do a proof of this formula later on. It behaves like a rectangle. What you can do is you can also try it. You have a big sector and then you minus a small sector. You can try that. But anyway though, let's continue with this. What we need is the width, which in our case is just the DL. And then the middle right here, we need to know the radius, which is the Y. Aha. So, have a look. If you find the area of this thing, that's just a small change in the surface area, and we'll label that as ds. And we just have to find this area right here. The length is going to be what? As we mentioned earlier, it's the circumference of this. The radius here is exactly the y right here. So we need to have 2 pi y, and then we have to multiply by the width, which in this case is the dl. Just like that. Keep in mind though, for the dl, we don't know which world we are in. It depends on the situation, right? So imagine you integrate. Here, if we have y as a function of x, then in that case, for the dl, we are going to use the version that we got earlier, and I'll write this down. Surface area will be the integral 2 pi y. 2 pi y stays the same. right? 2 pi y stays the same. But for the DL, I'm going to write down square root of 1 plus parentheses dy dx, and then square, and then we have the dx on the outside. Then you can see that we are in the x world. That means we have to look for the x value going from A to B. And we also have to be careful. X world, we have the y, which is not allowed. So make sure you substitute this right here for that, right? And then just make sure you do that when you set up your integral and then do the computation. Now, if we have x as a function of y, well, pretty much the same idea. Surface area equals the integral, and we have 2 pi y. Notice the 2 pi y stays the same. Whenever you rotate about the x-axis, 2 pi y is the vertical distance. That will be the radius that we are going to use. But if we have x as a function of y, we will multiply the square root of 1 plus dx dy and then square, and we will be in the y world. Now have a look. We are in the y world. Y is okay, so you don't have to do any change. And because we're in the y world, we have to go back here and see the y values. Let's say it goes from C to D. And this right here will complete the formula for that. Now, there's one more situation. What if we took the arc length right here, we took this arc and rotate about the y-axis? What do you think what the answer is? Triangle, triangle, triangle.